I'm going to try to prove Serre's theorem then. So we've fixed a root system and a base. And I'm using the notation Cij for the inner product alpha I, alpha j check. So these are the Cartan integers, or the Cartan matrix for this root system. And I'm using, as I said before, I'm using Humphrey's convention. I think more modern books transpose this matrix compared to the convention I'm following. Anyway, there we go. So here's the theorem, Serre's theorem. I think I called it Serre's theorem prime. Catchy name. It says let G be the Lie algebra with generators EI, HI, FI, I going from 1 up to L, and relations, I'll write them down below, then G is a finite dimensional semi-simple Lie algebra with maximal toral subalgebra T spanned generated by the H's, they commute, and corresponding root system was the root system we started with. Again, then I've got to quickly write down the Serre relations, so they're fairly easy. HI, HJ is 0. EI, FJ is delta IJ, HI. HI, EJ is CJI, EJ. And HI, FJ is minus CJI, FJ. And then the tricky ones, add EI to the 1 minus CJI over EJ is 0, and add FI to the 1 minus CJI of FJ is 0. So these two guys are for I not equal to J. And I think that was S1, S2, S3. Those are the easy Serre relations. And then the ones that are tricky, Sij plus and Sij minus. Those are the awkward ones. Okay, so that's what we're trying to do. And I'm just going to go kind of through the proof as swiftly as I can. I'm going to skip quite a lot of little steps along the way because, you know, it's kind of technical stuff, analyzing generators and relations. It's not. So proof part 1. So this is the consequences of S1 through S3, the easy relation. So we've got to analyze them first of all. So to do this, let's let G hat be generated by EI, HI, FI hat. I going from 1 up to L. Subject just to those first three relations, S1 through S3. So to understand G hat, how do you understand anything given by generators and relations? You find some representation, you find something it acts on. And so I'm going to make G hat act on the tensor algebra. So the free associative algebra, I'll just call it tensor algebra. The free associative algebra on L generators, so that's the tensor algebra on the vector space with basis x1 through xl. And I'm going to make G hat act on V. So I've got to write down how the generators act, and then of course you have to check relations. So I'm going to move on to the next slide. So I've got to tell you, maybe I can write one more thing here. V is spanned, in fact a basis. It's given by the monomials. So when I write xi1, xir, that r could be anything greater than or equal to 0. These guys, for all sequences I1 through IR from our index set, capital I, they give a basis for that tensor algebra. Okay, so that's the monomial basis. So I'm going to define the action of the generators of G hat on the basis. So H is going to act diagonally. So on monomial xi1, xir, it's going to act as minus ci1j plus cirj, just that scalar times xi1, xir. Fj hat is the easy one. It's going to just act by multiplying on the left by xj. And ej hat, well, this one's going to be defined recursively, so I'm going to act by ej hat on the stuff after the first term. So this is going to be defined recursively. So for that to make sense, I've got to tell you the base of that recursion. So I've got to tell you how ej hat acts on 1. That's the monomial when r is 0, and that's just 0. Maybe I should put dots in all of my actions to make it kind of clearer what's going on. Okay, I haven't quite finished the definition of ej hat. It's that recursive thing, and then delta, Kronecker delta I1j, and then the scalar ci2j plus cirj times xi2 xir. So this is really what ej hat's trying to do. It's trying to remove an xj out of this term. So if you have an xj right at the beginning, then that Kronecker delta is a 1, and you see it's basically crossed off that xj from the beginning, and it's given you this scalar. Otherwise, so that's that term. Otherwise, you just move the ej hat in, and you're sort of trying to recursively remove an xj from in that monomial that's left over. So hopefully that all makes sense. I guess the other thing is to note that you have to interpret this sum, the sum of these c's. This sum is 0 in the case that r is 0. Right, so if that monomial is actually the identity in this algebra, hj hat on 1 is just 0. And similarly down here, this sum here, you should interpret that as 0 in the case that r equals 1, because it's an empty sum then. Okay, so hopefully that makes it clear, this action. So now you have to check that the relations S1 to S3 hold, so that this action is well defined. So that's a sort of I'm going to leave that as an induction exercise. I always like leaving induction exercises to you, but I mean, for example, let's just maybe do one. If we wanted to check this thing, right, so that's one of the relations. So you have to take the left-hand side, the complicated side, and you have to act on monomial xi1 up to xir. So that's ej hat. So the fj hat just multiplies by xj. And then you have to subtract, well, the fj hat's just multiplying by xj. And then I've got to act with ej hat on the monomial. Okay, so that's all looking good. But now I'm going to use the definition of ej hat acting on that monomial. So I get it going inside, that's the recursive part, but when it goes inside, that recursive term just cancels out that term, right? So this is fairly easy. So all I'm left with is that part when it's it's eating up that xj at the beginning. So I get minus ci1j plus cirj xi1 up to xir, which is indeed the definition of hj hat on xi1, xir. Now, admittedly, I picked an easy one to give you as an example, but the other relations are similar. Well, they're left to you. Okay, so that's made a little beginning. So now we've got this Lie algebra G hat, and we've got some representation of it, this V. So now I'm going to use V. I'm going to use the action G hat on V to prove the first important step in the argument, which is that H1 hat up to HL hat span an L-dimensional abelian subalgebra, Lie subalgebra of G hat, and moreover, as a vector space, G hat decomposes as N hat minus. I need to name that subalgebra T hat. So there's T hat and then N hat plus, where this guy here, this is the subalgebra generated by E1, by the F's, sorry, minus is the F's, F1 hat up to FL hat, and this guy is the subalgebra generated by the E hats. Okay, so this is as a vector space. Okay, so I'm going to prove that. So we're going to use this representation. So let's maybe let phi from G hat to GL V be the representation defined above. So I'm going to first observe that phi restricted to T hat. So T hat, of course, yeah, where can I write it? Over here somewhere. T hat, that's the subalgebra spanned by the H's. In fact, it's an abelian subalgebra because of the relation S1, right? The H hats commute. So I'm going to show that this restriction of phi down to T hat is an injective linear map. So that will establish the first part, that first little part of the proof. Well, let's see how we do that. Let's say you've got something in the kernel. So it'll be some linear combination of those spanning vectors. If that's in the kernel of this Lie algebra homomorphism, all you do is you act on xi so the way hj hat acts on xi, it's just an eigenvector, so we just get this minus. So hj hat acts on it as cij, and then you just get that multiple of xi. So you deduce that this is 0 for all I. There's not really any point putting the minus out the front there. But right here, this is the Cartan matrix, which is invertible by the non-degeneracy of the form. Right, the Cartan matrix, well, it's not quite the Gram matrix. It's two different bases, the alpha i's and the alpha j checks. They're two different bases for the Euclidean space E, and the Cartan matrix is just the matrix gotten by pairing those two bases. Since the form's non-degenerate, that matrix is invertible. So you can solve this. You can multiply by the inverse matrix to deduce that aj is 0 for all j. And so the only things in the kernel are 0, so that establishes that injectivity. Okay, so we've proved the first part. Now, by the relations EI hat, HI hat, and FI hat span the quotient of the Lie algebra SL2 of C. Since hi hat is not 0 by what we've just done, it's not the 0 quotient, but SL2 of C is a simple Lie algebra. So we deduce that actually the span of EI hat, HI hat, and FI hat is three-dimensional and isomorphic to SL2 of C. So now I've got to show that this Lie algebra G hat is the vector space direct sum, as I wrote for n minus direct sum T hat, which we now understand direct sum n plus. Remember, n hat plus, that was the subalgebra generated by the e's, n hat minus was the subalgebra generated by the f's. So I'm going to introduce a little piece of notation here. Maybe I'll just write it for 4 guys. If you have 4 generators, A, B, C, and D, I'm just going to write them in a single bracket to mean the kind of multiple Lie bracket, A, B, C, D. This sort of right justified way of taking 4 generators and forming an element in, well, this notation makes sense even in the free Lie algebra. If you're looking at a free Lie algebra generated by a bunch of elements, these kind of right justified Lie monomials span that free Lie algebra. So if we're looking at n plus, it's spanned by these kind of Lie monomials in the EI hats and so on. Okay, so now you use induction on R. Of course, you need to use the relations that are in place S1 to S3, and then you just need the Jacobi identity. To prove a few more commutation relations, you need to be able to take one of these Lie monomials. So these are the guys that span this subalgebra n hat plus, and you want to know how to bracket that with an H. And it's an eigenvector, and the eigenvalue is just this CJI1 plus CJIR. And similarly for the F's, no surprises. Except for the minus sign. And then also you want to be able to bracket an F with one of these E monomials. We should all have hats on, there we go. And you don't need very much about that. You just need to know that it's in n hat plus if R is greater or equal to 2. And similarly, if you take an E and you bracket it with one of the F's monomials, that's in n hat minus if R is greater or equal to 2. Okay, so there's a little bit of work to just inductively check those things. They're not in any way difficult, just a induction drill. It follows that if you look at the sum of these subspaces, n hat minus plus t hat plus n hat plus, so the vector space sum of these subalgebras, this is actually a subalgebra. Right, you have to show that it's closed under the Lie bracket. So for example, you've got to show that something in n hat minus Lie bracketed with something in n hat plus is in here, and that'll follow using this identity. That shows that one of the generators of n hat minus on, well, all of the guys in n hat plus kind of degree 2 or more is in n hat plus. Of course, if it's just an F and a single F and a single E, that takes you into T hat. Finally, we need to show that the plus here, the vector space sum, is actually a vector space direct sum, but that's actually easy, but that follows by considering the decomposition into weight spaces. Right, so remember, eigenvectors in different eigenspaces are automatically linearly independent. So that's what's going to be used to show that these sums are direct. These and different generalized, these weight spaces, that's our generalization of eigenspace there. Okay, so that's that lemma. Okay, so now I'm going to let Eij hat be, well, the element from Sij plus the Serre relation. So this is add Ei 1 minus Cji on Ej hat. Similarly, there's Fij hat, which is add Fi hat to the 1 minus Cji Fj hat. This is all, of course, for I not equal to j. So these are elements of this Lie algebra G hat. And I've got to prove another technical lemma, namely that if you take some Ek hat and you bracket it with this Fij hat, or with F's and E's reversed, both similar, that's 0 for all k and for all I not equal to j. Okay, so let's quickly run through this. This is just a silly proof. So I'll just do the first. So let me see, if k is not equal to I, then that commutator is 0 by S3. And that means that add Ek hat and add Fi hat commute. So now I can calculate this guy, because Fij hat is a bunch of add Fi hats applied, and then I've got to apply an add Ek hat, but they commute. So I can just move it all around and do the add Fi hats out the front, and then do the add Ek hat inside. And well, that's already 0 if k doesn't equal j, but if k equals j, then it's equal to, what have I got? I've got add Fi hat to the 1 minus Cji, then that will be Hj hat. And I can do one of those Fi's, leaving the minus Cji of them, and Fi hat on Hj hat is, well, that's an Fi hat times the scalar. I think the scalar is minus Cji. So now there's two possibilities, right? It could be that Cji is 0. It's 0 because of the scalar. And if Cji is less than 0, well, it's obviously 0. Because we've got an Fi hat commuting with an Fi hat there, and so it's 0. So in all cases, it's 0. So that does k not equal to I, then k equals I. So here now, this is now an argument you should be kind of familiar with by now. So we're going to look at this SL2, Si, maybe I call it Si hat. So this is the SL2 spanned by Ei hat, Hi hat, and Fi hat, which we've shown is isomorphic to SL2 of C. And let me see, if you take Fj hat and you apply add Ei hat to it, it's 0 because I doesn't equal j. So this shows that this fj hat is a highest weight vector. For this SL2, Si hat, and its weight, so that's how Hi hat acts. Its weight is lambda, that's just minus Cji. Okay, so we've got this highest weight vector, and now you know this usual lemma that we have when we're acting on a highest weight vector, Fj hat. You can act with Fi hat to pull you down the string some number of times, maybe m times, and then if you act with Ei hat to go back up again, you know this lemma. It was way back when we were studying representation theory of SL2. You get m lambda minus m plus 1, add Fi hat one less time, Fj hat, and so it's 0 when the m is 1 minus Cji, which is exactly what we wanted, right? So because you get a 0 right here. Okay, that's a somewhat annoying lemma, but there we go. So now the second part of the proof of Serre's theorem. So these are the consequences of Sij plus minus. We're going to consider G, which is G hat over K, where K is the ideal generated by the Eij hat and the Fij hat for I not equal to J. So these are the elements that we need to throw in the extra Serre relations, Sij plus and minus, right? So we have to factor out those ideals. This is the Lie algebra that we're finally after, given by the Serre presentation. So maybe it's worth pointing out here that this G hat is almost always infinite dimensional here. I mean, I guess the root system A1 is a special case, and in that case there's no Serre relations, but otherwise this G hat's infinite dimensional, whereas this G is meant to be finite dimensional. So this K had better be killing a whole load of this Lie algebra G hat. So let me see, we need to understand this ideal K. So the next lemma tells you, so this is I guess lemma 3, says that K is I plus J, but I is the ideal of, maybe I won't write I plus J, that seems a little ugly. I'll write I minus plus I plus, where I minus is the ideal of n hat minus generated by the Fij hats, and I plus is the ideal of n hat plus generated by the Eij hats. Okay, so what I'm going to do for this is I'm going to show that I plus is actually, so by definition it's an ideal of n hat plus, but it's actually an ideal of G hat. And to do this, you just check its invariance under bracketing with all the generators of G hat. This is the usual sort of Jacobi type thing. The main point is that this uses lemma 2 in the end, because this I plus is generated by these Eij hats, and so when you have to prove that I plus is closed under bracketing with the Fk hats, that's exactly lemma 2. Similarly, I minus is actually an ideal of G hat. Then it follows, once you check that K is I minus plus I plus as the right hand side here contains all the generators. So now it's an ideal of G hat, and it contains all the generators of K, and so that does the job. Okay, so now from this, we've got our G hat, which we've proved is N hat minus direct sum T, direct sum N hat plus. Then we get that this G, which is G hat over I, is actually N hat minus over I minus T hat and N hat plus over I plus. So let's see, let's call this guy here N minus, we'll just call that T for short, and this guy here is going to be N plus. So we've now proved that our G is N minus direct sum T direct sum N plus, where those are the subalgebras generated by the F's. I'm just going to write Fi now for the image of F hat in G. T is exactly isomorphic to T hat, and N plus is the subalgebra generated by the EIs. Moreover, this T, it's the right dimension. It's this L-dimensional abelian Lie algebra spanned by H1 through HL. Okay, so we've made good progress there. Oh, one more thing to be said about this is that the SL2 of C argument made earlier shows also that this, if I just call it SI, the span of EI, HI, and FI, now down in G, this is isomorphic to SL2 of C. Okay, so that's the same argument because HI is non-zero and the relations hold. Okay, so we're really getting quite close now to the, I think, the most interesting part of the proof, actually, the decisive step. So let's see. For a weight lambda in T star, this L-dimensional Lie algebra's dual, I'm going to let G lambda, as usual, be the lambda weight space, so that's all x in G, such that Hx is lambda of Hx for all H in T. And of course, I'm going to identify my root system. So root alpha, I'm going to identify it with an element of T star in the usual way. So I want alpha of Hi to be the inner product alpha I check. Remember, the HI's correspond to those co-roots. Maybe that's a bit confusing right here. I've just right there that we started with a root system inside a Euclidean space. This form that I've used is the given form on the Euclidean space E that we started with. This alpha I check, it's the co-root of that root system. So now we come to kind of the decisive lemma, I think, lemma 4. It says that for a non-zero lambda in T star, that weight space, as I just defined, is non-zero if and only if lambda is actually a root, in which case G lambda is one-dimensional. So this really shows that for the first time that we have the kind of right-looking Cartan decomposition in front of us. In particular, it shows that G is finite dimensional because, of course, the dimension of G, it's the sum of the dimensions of all these non-zero weight spaces. They're all one-dimensional by the lemma, so that's the size of R, plus the size of T, which is L. And so for the first time, this lemma gives us that G is actually finite dimensional. We don't yet know that G is semi-simple, by the way. That'll come next. But at least this gives us that it's finite dimensional. So let's prove this. And actually, this is the most interesting and the most important place in the entire proof. So what I'm going to do is I'm going to consider add EI as a linear map from G to G. And my first claim is that this linear map is what's called locally nilpotent. That means for any vector in G, remember we haven't even shown G as finite dimensional yet, so maybe it's infinite dimensional, but I'm still claiming that for any vector V in G, some power of add EI kills that vector. So to prove this, I'm going to let M be just the union of the kernels of all of the powers of add EI. So we need to show that this M is all of G. That's exactly the claim. So to see this, you check that M is actually not just a subspace, it's actually a subalgebra of G. So you just have to take two vectors x and y killed by some powers of add EI and show that the Lie bracket of those vectors is killed by some power. So that's a kind of a Jacobi binomial type argument. I think you've seen that sort of argument before. And then you just note that all the generators of G lie in M, hence, yes, M is G as required. And how to see all the generators lie in there? Well, each of the EKs lie in M by the relation Sij plus. The FKs lie in M by the other Serre relations. I think you need S3 for that, and so therefore the HKs lie in M by S2. Okay, so add EI is locally nilpotent. Why is that important? Well, because that's what you need for it to make sense, to define a linear map. Exp add EI. So this is just the exponential power series applied to the linear map add EI. So add EI squared over 2 factorial, add EI cubed over 3 factorial, and so on, right? So that's a well-defined linear map from G to G, because on any vector of G, all of these linear maps, well, after a while, they're all just zero. So this infinite sum becomes a finite sum when you evaluate on any given vector, right? So that's just exponentiating that linear map, exponentiating that matrix. It makes sense because that linear map is locally nilpotent. If G was finite dimensional, of course, it would make sense anyway, but we haven't checked that. So I need that argument of local nilpotency. In fact, it's an invertible linear map. It's an automorphism because the inverse is just exponentiating minus add EI. So that's just formal properties of the exponential series there. So I've done it for EI up above, but of course the same arguments apply to Fi. So we can define what I'm going to call sigma I. So it's exp add EI, exp add minus Fi, exp add EI. So that's a linear map from G to G. And so now, well, so this maybe has come a bit out of the blue. It's the first time you've seen exponentiation. So this is something I'm going to discuss in week 10 in reasonable amount of detail. So I'm not going to spell out how you show this next step, because you'll see it next week. You show that when you apply this linear map to the subspace G lambda, you get G Si of lambda. And so right here, this is the Si in the Weil group, the simple reflection, coming from our root system. Remember, Si of lambda, it's lambda minus lambda alpha I check alpha I. Okay, so that's showing, because there's this invertible linear map taking g lambda to g si lambda, it shows that these two different weight spaces have the same dimension. But that implies that, in fact, you can take any element of the Weyl group, right? Because the Weyl group's generated by those SIs. Okay, so now we can prove the lemma. G alpha I is one-dimensional. It's just spanned by EI. That's easy. It's even true in the G hat that I constructed earlier. Since every root is conjugate under the Weyl group to a simple root, it follows that dim G alpha is 1 for all alpha in the root system. Why is every root conjugate to a simple root? I think we showed that in the last chapter. Oh, no, we showed that every root lies in a base and all bases are conjugate. Putting those together, every root is conjugate to a simple root. Similarly, you see that the dimension of G C alpha is 0 unless C is plus or minus 1. This is for a root alpha. But so you do the same sort of argument. You reduce to showing it for the simple roots, and it's easy to see that if alpha is alpha I, this statement holds. Finally, we need to show that the dimension of G lambda is 0 for lambda in T star that's not a multiple of any root. So here I'm just going to leave this as a little exercise. So I guess the first thing that's obvious is that if G lambda is non-zero for such a lambda, then certainly lambda has got to be a sum of simple roots with Ci in Z, because the generators Ei and Fi, they're just alpha i's and minus alpha i's, and so any monomial is just going to be a Z linear combination of them. Actually, even a little bit better, you either have all Ci's being greater than or equal to 0, or all Ci's being less than or equal to 0. This follows because G is n minus direct sum T direct sum n plus, right? So everything in n minus is going to involve only negative linear combination of alpha i's, and the stuff in n plus is going to be only positive linear combination of alpha i's. And so now you just appeal to the exercise that I'm going to give you. So let me see, it's homework 8, question 6, I think I've put this exercise. It says that if you've got lambda, some linear combination of simple roots with all the Ci's being natural numbers, and it's not a multiple of any root, then you can find an element of the Weyl group, so that if you conjugate lambda by W, it has both positive and negative coefficients when written in terms of the simple roots. Right, so this does what we need, right? Because some weight with both positive and negative coefficients, well, that weight space of G is 0, And so it follows that the lambda weight space is 0, and that's what we need to complete the proof. Okay, so with that lemma now we can complete the proof of Serre's theorem. So what we've got to do is we've got to show that our Lie algebra G, which we've now shown is finite dimensional, let's show that it's semi-simple. So for this, it suffices to show that any abelian ideal A of G is 0. That checks semi-simplicity. So the point about this is that A is its intersection with T, direct sum its intersection with all the G alphas, and we've shown they're all one-dimensional and are labeled by the roots. This is just because G itself is completely reducible as an add T module. A being an ideal is an add T submodule. So A is completely reducible. That's just exactly showing that A is this direct sum of its T weight spaces. If sum A intersect G alpha is non-zero, well, that's just saying that G alpha lies in A. But A is invariant under those sigma i's that I defined before, right? Because it's an ideal, and the sigma i's are just applying add of ei or add of minus fi to it. So yep, A is invariant under those sigma i's. So once you've got some G alpha in A, you get that all G, well, you get that, let me see if I can say this right. So once you've got some G alpha in A, you get that some G alpha I is in A. So that gives you an EI is in our ideal, but then you bracket with Fi to get that. So once you've got EI in there, you get HI, and you bracket again, you get that those are in A, but that contradicts A being abelian, because we know these guys generate an SL2, which is not abelian. Okay, so this shows that A actually lies inside the torus, but also because you could bracket A with G alpha, and that would, so that has to be 0, otherwise you'd get some G alpha in there. So this shows that actually A doesn't just lie in T, it lies in the kernel of alpha. In fact, the intersection of those over all roots, but that's just 0. Okay, so that's checked that G is a semi-simple Lie algebra. And I think we're basically done. I think the final little step, right? So we've got the right looking Cartan decomposition. The roots is R. I think the final little step is to identify the form on T star coming from the killing form with the original form coming from E. Well, they're not going to be the same, but we've got to show that they're the same up to rescaling on each indecomposable component, because that's what isomorphism of root systems corresponds to. But you see the killing form, we see kappa of Hi, Hj, so that's just traced, right? So it's going to be the sum of all roots of alpha of Hi alpha of hj. This is just directly calculating trace. So the killing form on T star is going to satisfy this. Right, alpha of hi, it's alpha I check. By the way, I identified the root system with elements of H star earlier. So now we've got these two different forms on T star. We've got the form coming from the Euclidean space at the beginning E, and we've got this killing form coming from our Lie algebra, right? And this is the relationship between those two. So they're not the same form. It remains to observe that kappa on T star, well, I guess, so now we've got a semi-simple Lie algebra, right? This is its killing form. It gives us an inner product on E. It's just given explicitly in terms of the original inner product on E by this formula. So it'll just be kappa. Okay, let me write this. It'll be this form. It'll be the sum alpha in R, alpha lambda, alpha mu. And I mean, if you're worried to see that this is W invariant, the original form on E was W invariant, and so it's easy to see from that formula that the kappa is W invariant. But each, so such a form is unique up to rescaling by some positive real number on each indecomposable component. That's due to the irreducibility of E as an RW module when the root system is indecomposable. Okay, so maybe I'm going a little bit too quickly through the argument at the end there, but that's Serre's theorem.